Hi everybody, welcome back to another video on Feynman integration. Today we're going to be evaluating kind of a famous integral. I believe this integral was presented to Richard Feynman as a joke, but he ended up solving it. The integral is the integral from negative infinity to infinity of e to the negative x squared over x squared plus 1 dx. And that integral cannot be solved using traditional techniques. One thing we're going to have to use for this video is the error function. The error function is something I like to call, it's a cheat function. It's not an elementary function. It has no elementary representation, but it is considered to be a legitimate function in many scientific fields, specifically like statistics and things like that. Anyway, the error function is defined to be, it's defined such that ERF, error function, of some value z is equal to 2 over the square root of pi times the integral from 0 to z of e to the negative x squared dx. So for instance, ERF of 7 would be 2 over the square root of pi times the integral from 0 to 7 of e to the negative x squared dx. So like I said, that's kind of a cheap, it's a cheat function, not a cheap function, it's a cheat function. In that you're really, we're saying that this is as far as you can go with that. But anyway, it's considered legitimate. Like always, we will, to solve this integral, start by creating a function of t that closely resembles our original integral. In this case, all I'm doing is I'm putting a t squared in front of that x squared to give us f of t being equal to the integral from, that should be negative infinity to infinity. Let me fix that really quick. Obviously, that integral right there would simply evaluate to 0. Negative, there we go. Did I do that anywhere else? No, I don't believe I did. Okay. So yeah, our function of t is the integral from negative infinity to infinity of e to the negative t squared x squared over x squared plus 1 dx. And we note that f of 1 is equal to our original integral I, and that f of 0 will be equal to pi. If you plug in 0 for t right there, you'll get e to the 0, which is 1, leaving you with simply the integral from negative infinity to infinity of 1 over x squared plus 1 dx, which evaluates to pi. Our next step is to take a derivative of f of t with respect to t using the Leibniz rule, by simply taking a partial with respect to t of that integrand right there. And what you get if you do that is that f prime of t is equal to negative 2t times the integral from negative infinity to infinity of x squared e to the negative t squared x squared over x squared plus 1 dx. And we're just going to perform kind of a little rewrite of that. Right here, what we do is we put a parentheses around that x squared and add a 1 inside of it right here. That has the effect of really subtracting negative 2t times the integral from negative infinity to infinity of e to the negative t squared x squared over x squared plus 1 dx. So we have to add that back, and that's what I did. And then I made a little note here that if you evaluate this integral, you will get negative 2 times the square root of pi. And I also noted right here that this thing, this integral from negative infinity of this junk, is simply our f of t. So, using all that, we get that f prime of t is simply equal to negative 2 pi plus 2t f of t. And I had that written right there. And now A lot of you would recognize that as a differential equation on a function of t. That's great if you do. We're going to make it so that you don't actually have to have a background in differential equations to solve that. And we're just going to right away multiply both sides of this equation by e to the negative t squared. And what you get if you do that is that f prime of t times e to the negative t squared minus 2t e to the negative t squared times f of t is equal to negative 2 pi e to the negative t squared. And I hope you can see that. All I did was multiply this by e to the negative t squared and then both of these terms by e to the negative t squared and did some rearranging to arrive at this. And then we notice that this part right here, this f prime of t times e to the negative t squared minus 2t e to the negative t squared f of t, looks like the result of a product rule for derivatives, and it is. That is why I multiplied both sides of the equation by e to the negative t squared, is so that, specifically so that that would be the result of a product rule. That is a trick called creating, I believe it's called an integrating factor that you learn about in differential equations, but I'm not going to get into that. Anyway, your integrating factor in that case would be e to the negative t squared. So that's why I multiplied both sides by that. So then I just rewrote this part right here as f of t times e to the negative t squared prime. That's not to the first power, that's prime. I realize I probably should have written that d dt f of t e to the negative t squared, but I didn't. Anyway, you can see that if you take the derivative of this function of t right there with respect to t, you have to use the product rule. And what you get is you get the derivative of the first right there, f prime of t, that is the derivative of the first, times the second, e to the negative t squared, right there, e to the negative t squared, plus the derivative of the second. The derivative of the second you can see right here. It is negative 2t e to the negative t squared times the first, f of t. So that's how I justify writing it that way, because it is the result of a product rule when you take the derivative with respect to t of that equation right there. So now we know that this is valid, and if it's valid for all t, it's valid for all x. So I just rewrote that right down there, just replacing t with x. Let me gather my thoughts here. Right. I know what I did. So, now what we want to do is take and integrate both sides of this equation from 0 to t dt. Sorry for my writing, but you know that's something you can do. That's valid. Since this is equal to this, then you can integrate both sides of the equation from 0 to t with respect to t. And what happens if you do that is this. If you evaluate f of x e to the negative x squared prime dt from 0 to t, you have to remember the fundamental theorem of calculus. Basically, this is going to be the antiderivative of the function evaluated at t minus the antiderivative of the function evaluated at 0. Now, the antiderivative of a derivative, which this is a derivative inside that integral, The antiderivative of that will simply be the function itself. So what we'll be left with is f of t e to the negative t squared. That would be our big F evaluated at t, minus f of 0 e to the negative 0, which would simply be f of 0, which, as we noted right here, is simply pi. I'm sorry this is so confusing, and I'm kind of skipping some of the steps. I hope you're following this. I think if you're having trouble, pause it, rewind it, and watch it again. It took me a little while to wrap my head around this one myself. But anyway, I hope I've been clear enough. So we're at this step right here. F of t times e to the negative t squared minus pi is equal to this thing right here. And I did some weird math right here, as you can see, but it's all valid. You already have the negative 2 square root of pi, and then I simply multiplied it by the square root of pi over 2, and then multiplied it again by 2 over the square root of pi. So basically, I multiplied it by 1. And I just did that to help you visualize what's going on, because you'll notice that this right here, 2 over the square root of pi times the integral from 0 to t of e to the negative x squared dx, is simply ERF of t. And that's why I did that. And then you notice that the square root of pi times the square root of pi is pi, and these 2's will cancel out. Then subtracting pi from both sides of the equation and multiplying both sides by e to the t squared gives us a final result for f of t being equal to pi times e to the t squared, all of that times 1 minus ERF of t. So there it is. There is our function of t. And it uses that thing I said about earlier about a cheat function. Pure mathematicians don't really like to use that, but if it was good enough for Richard Feynman, it's good enough for me. So anyway, we have our f of t. So now all we have to do is plug 1 into that to find the answer to that integral. And what we get if we plug 1 into that equation is that I is equal to pi times e to the 1, which is simply e, times 1 minus ERF of 1. And I hope that was clear enough. Like I said, go ahead and rewind that video, pause it, verify my work. There was a lot of work involved in this, a lot of room for mistakes, and I am not perfect by any means. But anyway, yeah, that problem right there was presented to Richard Feynman as a joke, saying, oh, you think you're so good, go ahead and solve that one. Well, he did. Admittedly, he used the error function. He wrote it in terms of the error function, which, like I said, a lot of mathematicians don't consider legit. But anyway, that's it. That's the answer. I is equal to pi e times 1 minus ERF of 1. Hope you enjoyed that.